This video will focus on the calculation of the ship's latitude using the Ex-meridian method when moon is the celestial body. So previous videos on the same topic, that is Ex-meridian, have explained this method when we used the sun, the stars and the planets as an example. So I thought today's video should focus on moon so that you can also learn how to use the moon as a celestial body and obtain the latitude using the Ex-meridian method when you are on the ship. Alright, so we'll start with the question, but before I start with the question, if you don't know what Ex-meridian is, Ex-meridian refers to the point when you have missed the meridian passage. So meridian passage is the point when the celestial body is meridian and your celestial meridian. So you means you are the observer on the ship. If your position is projected onto the celestial sphere, so if your meridian on the celestial sphere and the celestial body's meridian on the celestial sphere, they align, that is the meridian passage. And that happens only at a particular time. Now if you miss that time, then you can use the Ex-meridian method. So both the meridian passage and Ex-meridian method can be used to find the ship's latitude. That's called the observed latitude. Ex-meridian is also used just before the meridian passage also. So if you predict that maybe at the time of the meridian passage it could be cloudy and you will not be able to observe the celestial body, you can use it just before the meridian passage. So the key thing here is that the celestial body's meridian should be very close to your meridian or your celestial meridian as an observer. Alright, so let's get into the question. The question says it's 29th of November 92. The dead reckoning position, the DR position or the estimated position is 36.8 south, 96.40 east. The sextant altitude of the moon's upper limb, that's the key word here. So UL stands for upper limb, near the meridian. So whenever you see near the meridian, that means the question is referring to an Ex-meridian method. Alright. So the sextant altitude near the meridian of the moon's upper limb was 68 degrees 53.7 minutes. The chronometer time was 9 hours 18 minutes 24 seconds. The chronometer error was 5 minutes 1 second slow. Height of eye is given as 14 meters. Index error 0.2 of the arc. And what you have to find is basically the direction of the position line, also called PL, and a position through which the position line passes. So when we say position, we are referring to the observed latitude that you will calculate using the Ex-meridian method, and the DR longitude, because we are going to use the same DR longitude. Alright, so let's get into the solution. The solution starts just like if you have watched all my previous videos, you must have seen that all my videos, they start with the solving of the ambiguity of the chronometer time. So I have given you an explanation on what the ambiguity of chronometer time is. If not, please watch my other videos. Also, there is a separate video titled Ambiguity of the Chronometer Time, so you will understand this better. But just for the benefit of those who are watching this video for the first time and you have not watched my other videos, let me solve or let me explain quickly what is ambiguity of the chronometer time. So basically, when the chronometer time is given to you in the question, to find out the correct chronometer time, you will add 12 hours to the hour and get two options. That's the reason is because the chronometer is a device on the ship's bridge that gives you the GMT time. But GMT time could be different from the time on your ship because you may not be anywhere close to the GMT, and so could be the date. So sometimes the date at GMT could be different from the date on your ship, depends on your longitude. So the further away you are from the GMT, if you are in the east longitude, your time will be more than the time at GMT. If you are in west longitude, the GMT time will be more than your time. Alright, so you have to write down both the options and now figure out which is the correct GMT time. So add 12 hours to the R column and then add your error, which is given as slow. This is given to us in the question as 5 minutes 1 second slow. Add the error in both the cases, get both the options, and then you get two options for GMT. What is 9 hours 23 minutes 25 seconds, or it could be 21 hours 23 minutes 25 seconds. To resolve this, we apply a correction called the LIT. The LIT stands for longitude in time. And how do you get LIT? Well, you just divide the DR longitude by 15. So the DR longitude is given to you in the question as 96 degrees 40 minutes. Just divide it by 15, you will get 6 hours 26 minutes and 40 seconds. Now if you have seen my other videos, I normally convert the LIT into something called the zone, which is a practical way of timekeeping. But today I'll not be doing so. I'll tell you why. I'll tell you the reason very soon. We'll go on and resolve the question, and then I'll tell you why I have not changed the LIT into zone today. Alright, so I will put this LIT here, and in both the cases I will add the LIT, because when we are in east longitude, the time on my ship, that is the local mean time based on the meridian of my ship, is more than the time at the GMT. So as we move away from GMT towards east, we add hours. So the local mean time on my ship, which is based on my longitude, individual longitude, will be more than the time at GMT. Alright, so when I add 6 hours 26 minutes 40 seconds the LIT to both the GMTs, I get two options again of the LMT, which stands for local mean time. Now, how do I know which is the correct GMT or which is the correct LMT? Is there a hint given to me in the question? Now in the question there is no hint given to me. Normally in the question they give you a hint like it's AM or it's PM or it's morning or it's evening or something like that. But today in the question there is no hint. So I'll have to figure out which is the correct GMT time. And to do that I'll have to use the LMT as a hint. Alright. So this is a moon question. So I will go into the nautical almanac for 29th of July or 29th of November, sorry, that's the date given to me, and find out what is the moon rise and what is the moon set time. And then from there I can get an idea of when the meridian passage may have been occurring. Let's go and I'll explain it further. So I'll go into the 1992 nautical almanac, and you can see here is the 1992 nautical almanac, and I'll use the red pen here so you can see. So this is 1992, this is 29th of November. Over here you have the moon rise time, over here you have the moon set time, right? This is for 29th of November, 30th of November, 1st of December. Now for my latitude, which is 36 degrees something minutes south, this is south, right? As I go down it's south. So somewhere here, my moon rise time on the 29th is about 9:12. That is the local mean time. So all these times are given in local mean time. And the sunset time, or rather the moon set time for the same latitude will be around on the 29th about 22:57. So things are occurring between 9:12 to 22:57 local mean time. Alright, so if I go back to the solution, the meridian passage should also occur somewhere between 9:12 to 22:12. Now 3 hours 50 minutes 5 seconds, this local mean time here, there is nothing between there. So everything starting at 9 and then finishing by 2200 hours. Local mean time, right? So therefore the meridian passage, when the moon's meridian aligns with my meridian as an observer, should occur between 9 to 2200. So therefore this cannot be the correct case. The LMT of 15 hours is when the meridian passage of the moon may have occurred, because it occurs between 9 o'clock in the morning to 2200 hours LMT. Alright, that's the only hint I can, and that's an estimation I'm doing. So I have not yet found out the exact time of the moon's meridian passage, but I can get an idea. Therefore my correct GMT, so this will be 29th, because I know it's 29th of November on my ship, and since I am only adding 6 hours to the GMT, I know that even at GMT the date is still the same. So then this becomes my GMT time, date and time, 29th of November, 9 hours 23 minutes and 25 seconds. Alright, so this is the time I'll be using to resolve the rest of the question. So I will be going to the nautical almanac and finding out the GHA of moon for 9 hours, which is here. The increment will be for 23 minutes and 25 seconds from the nautical almanac again. The V value I will also get, I will show you where I get it from. The increment is always added as the word suggests, and in this case the V value is positive, so I will add this as well, and then I get my GHA corrected. Alright, so I'll show you where I get these values from. So I'll show you where I got the V correction from for a V value of 13.7. Then I'll also show you where I get my declination from for 9 hours. How do I get my D value, and where do I get my D correction value of 3.6 as well. And then this will be for 23 minutes and 25 seconds, and then this will be for 9 hours 23 minutes 25 seconds. Alright, so let's start with the GHA for 9 hours, and I'll show you what all things I can get from there. Alright, so I'll go back into the nautical almanac. This is 29th of November, and GHA for 9 hours. So you see here the GMT time is given here on the extreme left hand side, and the vertical column is all the hours. So this is for 9 hours. If I go horizontally, moon is here. So the GHA of moon, the V value, the declination, the D value, and the horizontal parallax, that's HP. You can get all these values at one go. So if you see, this is the GHA 256 9.9, the V value is 13.7, it's a positive value. The declination is 15 degrees 12.8 south, the D value is 9.2, and the horizontal parallax or HP value is 54.7. Alright, so if you can remember these 5 values, that will be great. Otherwise, just write it down in a paper, because I'm trying to save some time here. Instead of going back and forth from the Nautical Almanac into the page where I'm doing the solution, you can pause the video at this point if you want, and then note down all the values that you can get from one go, and then I will show you where I got the rest of the values from. Alright, so I'll go back into the solution, and you can see these are the values I have used. The GHA, the increment, the increment I have not got yet. So I've shown you the GHA, I've shown you the V value of 13.7, I've shown you the declination 15 degrees 12.8, and I've shown you the D value. Right? So now I have to show you where I get the increment from, and the V correction for the V value, and the D correction for the D value. So I also have to remember some of these values, 13.7 and 9.2. So I better write this down, because I'll also forget otherwise. So V is 13.7 and D is minus 9.2. The increment will be for 23 minutes and 25 seconds. Right? So I'll go back into the Nautical Almanac, and I have to go into the increments page for 23 minutes, and so this is here. Alright, so 23 minutes, and this is 23 minutes, this is 25 seconds will be in the vertical column here, right? The increment for moon is here, 535.2. The V correction for a V value of 13.7, you can get it from these columns here. So for 13.7 you get a V correction of 5.4, and for D value of 9.2 you get from here 3.6. So V and D correction values are obtained from the same column. It depends on the value. Alright, so the D correction was negative, that's why the D value was negative, so you will apply a negative D correction. And the V value was positive, so you will apply a positive V correction. Alright, at this point of time, again you can pause the video. If you are thinking I'm rushing through, just pause it and see where I'm getting the values from, and then you can go back and resume the video and start the solution. Alright, the reason I show you at one point of time is otherwise we are back and forth from the solution to the Nautical Almanac, and it takes longer time and you guys might get confused. Alright, so I've gone back into the solution. Now I've shown you where I got the increment from, the V value from, and the D correction from. Alright, negative will be D correction because the D value was negative, and then you get a corrected declination, and so declination is done. And GHA, of course, you add them and then you get the GHA, and then you have a east longitude. So when you have east longitude, the rule of thumb is longitude east, GHA is least. That means whenever it's east longitude, you will add your longitude. So the rule is longitude east and GHA is least. Alright, compared to GHA is least compared to LHA. So LHA should be greater. And that's why you will add the longitude to the GHA. And when you add the longitude to the GHA, you get the LHA of 358, 30.5 minutes. Alright, that's the rule. Now I'll erase this because I have to write something else here. Just you can pause it or you can rewind it and then see it. I say rewind because I'm still used to those tape things. You can just go back on the video. Alright, so LHA here has to be named. In this case, I will name LHA East. Why? Because the rule is LHA, if LHA is between 0 to 180, LHA is named West. If it is greater than 180 to 360, LHA is named East. So in this case, you will name your LHA East. And this comes handy later on when we are calculating our bearing. Alright. Once we've done that, we start calculating the true altitude from the sextant altitude. So the sextant altitude is given to us in the question as 68 degrees 53.7. Then the index error given to us again in the question is off the arc. Whenever it's off the arc, you will add the index error, 0.2 minutes, add the index error. Then the height of eye given is 14 meters. So we'll find out the height of eye correction, which is always negative for 14 meters. So we'll go back and I will go into a separate table for moon. When it comes to moon, okay, so the moon tables are here. So if you can see, the height of I will be somewhere here. Okay, so the height of I is somewhere here. So 14 meters will be somewhere here. Alright, so if I can show you with a red pen, 14 meters is somewhere between 13.8 and 14.2. This is the height of I, dip, and the height of I is meters here, and that's why your correction is minus 6.6. Alright, so this is your height of I table. There is also one table given in the 3rd or 4th page of the nautical almanac, but for moon we just use this table because this comes in handy. We can find out the rest of the values as well. So the height of I is given here, that's known as the dip, and it's given in meters and feet. So in this case, of course, your height of I is 14 meters, which will be between 13.8 and 14.2, so you get minus 6.6. So if we go back again in the solution, and then I'll show you where I got the rest of the values from. So you can see the height of I is minus 6.6. You apply the negative correction, get the apparent altitude. So it's sextant altitude, you apply the indexer, you get observed altitude. To that you apply the dip, you get apparent altitude. So I've written the acronyms here. These are not standard acronyms, but I'm just letting you know what they stand for, just in case if you guys get confused with what I have written here. And then you have to find something called the main correction, which is added here, positive. And then horizontal, for a horizontal parallax of 54.7. You remember where we got this from? From the very first page when we are getting our GHA and declination. Remember I showed you the horizontal parallax value, it was 54.7. So we use these values. So for apparent altitude of 68 degrees 47.3, and for a horizontal parallax of 54.7, we'll have to go back into the tables and get some correction. Alright, so we'll go back into these tables, the one that I showed you. Now these tables, if you're wondering where these are from, these are actually in the nautical almanac. I've just saved them separately because I'm using digital copies here, and it's easier for me to just work on the separate document. Otherwise this is part of your nautical almanac, and it's towards the end. These are last few pages. It's titled altitude correction tables for moon. Alright, so for an apparent altitude of 68 degrees and 47.3, now you can see here is your apparent altitude values, and this goes up to 34. So we have to go into the next page. So I will go into the next page here, and then 68 degrees 47.3. So you can see apparent altitude values, the degrees are in horizontal column here. So 65 to 69 is here, so that means 68 is here, and the minutes are in the vertical column here, and I am interested in 47.3, which is very close to 50. So I will come here. Alright, is 31.3, and then for a horizontal parallax of 54.7, which will be, this is the horizontal parallax values. Alright, so 54.7 will be somewhere between here and here. So if I go between them and then stop in under the column where is my apparent altitude, I need it for upper limb. Remember, so it's moon's upper limb. This is upper, this is lower. So 54.7, somewhere around here, 3.3 will be somewhere, that will be the value. Alright, and this will be 31.3, very close to 31.3 or 31.2. You can just do some interpolation if you want, otherwise don't worry about it. The other thing that I have to show you here is whenever it's upper limb, and I'll show you that in the solution also. You can see there are some instructions given here that whenever it's upper limb, you have to subtract 30 minutes. It's only in the case of upper limb. So that will be after you apply these corrections. Alright, so this is corrections, this is part of it. So when I go back to the solution, you can see that the main correction is 31.2 with little interpolation. The horizontal parallax correction is 3.3 as I showed you, and when you add all the values together, you get 69 degrees 21.8, and then I have applied the upper limb correction of 30 minutes as instructed in the nautical almanac. So when I apply that, I get a true altitude value of 68 degrees 51.8 minutes. Alright, now I have named this north. I will tell you how I named this later on when I come back to, I'll come back to this, don't worry. Alright, so when I get a true altitude, just subtract it from 90 degrees, and then you get something called the true zenith distance. So this stands for TZX. In some books it also says TZD. This stands for true zenith distance. So you subtract it from 90 degrees and you will get 21 degrees 8.2, and you can see I have named it south here. Now again I'll come back to this later on. So normally when I start naming this, I'll come back to it. Alright, because this is not the value we'll be using to calculate our latitude, but I'll tell you why it is important. Now the true zenith distance, although I will not use it to calculate the latitude, I need it for this formula here because I need to find something called MZX, or sometimes in some books they write it as MZD. Now MZX or MZD stands for meridional zenith distance. Alright, so if my pronunciation is not very good, this is how it's pronounced. Alright, or this is how it's written, MERIDIONAL, meridional zenith distance. This basically means the angular distance between the observer's zenith and the celestial body. So if your body is projected onto the celestial sphere, it's called observer zenith, and the angular distance between you and the celestial body when you are on this almost on the same meridian and your meridians are aligned, that's called meridional zenith distance. Happens very close to the meridian passage time. Now that formula is cos tzx plus 1 minus cos of LHA or P, you can call it P or LHA, and it's times cos of lat and cos of declination. Alright, so cos of lat and cos of declination, all you have to do is basically put in the values here. So put in the values of the tzx, put in the value of the LHA, and put in the value of the lat and declination in the formula. Alright, make sure you adhere to the rules of BODMAS or division, multiplication, subtraction. See what I have done and try to resolve the bracket first and then multiply it by cos of lat and cos of dec. Get the figures in the bracket first. Alright, brackets always come first, and then get this value. Take cos to the other side, becomes cos inverse, and cos inverse of this value will give you a meridional zenith distance or mzx value of 21 degrees 5.7. Alright, now I'll come back to how I was naming these. So when you, and I'll start from true altitude here. So remember, true altitude above, I named it north. It's named north because it's named same as bearing. Now what does that mean? That means is if the celestial body is almost on my meridian when I am the observer, I can just assume that they are very close to the meridian, very close to my meridian. So what I'll do is I'll plot the celestial equator first, which is called the equinoctial. So it's denoted by Q. This is equinoctial denoted by Q. Alright, now we are in the celestial sphere, right? You are also in the celestial sphere. Now what is your latitude? Your latitude is 36 degrees 14.9 minutes south. So you will go south of the celestial equator as we do in the Earth sphere. We just, if we are in the southern hemisphere, we plot our position south of the equator, right? And you denote yourself by Z. This is U, zenith. Alright, I'll also draw a little U if you want. This is you as the observer. And then you plot the latitude of the celestial body. Now latitude of the celestial body is called declination. Alright, and which is 15 degrees 9.2 south. So body will be here. So if this is 15 degrees 9.2 south, this is the declination, right? South. And this here is the latitude, which is 36 degrees 14.9 minutes south. And this is the celestial body. This is the moon. So that means the moon is bearing north from you, right? And that's why when we say we name true altitude same as bearing, we will name the true altitude north. Now true zenith distance after that, which you get after subtracting 90 degrees as you did above, you name it opposite to true altitude. So if you have named true altitude north, you will name it south. Alright, it says so here. And the meridional zenith distance is named in the similar way. You name it opposite to the true altitude. So that's why I have named it south. After this, I don't need the value of the true zenith distance. So that's why I will remove it. This was just to get the value of the mzx. Once you get mzx, write down the declination. When you write down the declination, the rule is same names add, different names subtract. So if they are same names, mzx and declination, that is if they are both south, if they are both north, you will add it. If the one was south, the other was north, you would have subtracted it. Alright, both are same names, you add it. When you add the two, retain the name of the larger or retain the name, since in this case both of them are south, you take the south and you put the south here. Your latitude is south, and when you add it, you get the value. That's your observed latitude. This is not your DR latitude, this is the observed latitude. Observed latitude is more accurate, DR latitude is estimated. And then put down your DR longitude. This becomes one of your answer. This is the position through which the position line will pass. Alright, then you have to find out the position line. To do that, just calculate the component of A by dividing tan lat by tan LHA. Put in the value of the latitude and the LHA. Alright, and then you get 28.1. If you are getting any negative sign in the calculator, just ignore the negative sign. Alright, don't include negative signs, but you have to name it. So you named A north. Why? Because it is normally named opposite to latitude unless your LH is between 90 and 270. In this case, your LH is not between 90 and 270. So you will name it opposite to lat. So if your lat is south, you will name it north. Alright, Now here I normally stick to 1 to 2 decimal places, depends on what your lecturer wants or what you are used to. You can go more if you want. Many books go up to 5, 6 decimal places. The more the decimal places, the more accurate it is. I am just keeping to 1 decimal place in this case. It's completely up to you what you do. You might get a slightly different answer from mine depending on the number of decimal places, but don't be stressed about it. You might be more accurate. If the more the number of decimal places, the more accurate you become. So once you calculate A, calculate the component of B by dividing tan of declination by sine of LHA. Put in the values. Again, if you are getting a negative sign, ignore the negative sign when you are finally writing down the answer. So A, B, C, they cannot be negative. Alright, you have to write a positive value, but you have to name it. In this case, you name it south. Why? Because B is named same as declination. So your declination was south, you will name B south. But do not include any negative sign in the value of A and B. Alright, in the final value of A and B. Alright, over here, there cannot be no negative sign in the final value, like 10.4 and 28 1 point cannot be negative. Alright, here if you are getting somewhere in this portion, if you are getting negative value, then retain it. If this portion you are getting negative value, then you retain it. Only in the final one, no negative values. Alright, then you write A and B values here, include the signs. The rule is if they are different names, you will subtract it. If they were same names, you would have added it. In this case, they are different names, they are north and south. If they were same names like south and south and north, you would have added them. But in this case, they are different names. Subtract it and take the name of the larger. So retain the name of larger for C. So A was larger, it was north, so you will call C north. And after subtracting it, just always subtract the smaller number from the bigger number. You get 17.7 and that's north, that's C. Then you calculate the last bit, which is tan of azimuth or tan of bearing equals 1 by C multiplied by cos of lat. Put in the values of C and cos of lat, resolve the denominator, then divide 1 by it. This is what you will get. Take the tan to the other side, it becomes tan inverse of the value. I am using 5 decimal places, you can use more if you want. The more the decimal places, the more accurate it is. And then you get a value of 4 degrees, which you can see I have named north and east, making the bearing 004 degrees, because northeast 4 degrees is 004. Now where did I get my north and east from? Well, north I got from C. Name of C. Whatever was my C, I will put here. If it was south, I would have put south. Because it is north, I have put north. E I have got from my LHA. Remember, we named the LHA before earlier east. So I will name it east. North 4 degrees east means if this is north and 000, this is east and this is 090, you are going 4 degrees from north towards east. And that's why if this is 4 degrees, your true bearing is 004 degrees. So that's why your bearing becomes 004 degrees true. But that's not your position line, but you can get the position line from it. If you subtract 90 from it and if you add 90 to it. So if you add 90 to it, it's pretty simple. You get 094. But how can you subtract 90 from 004? You will get minus 86. No, it's not that case. So what you will do is basically, if you are trying to subtract a bigger number from a smaller number, in this case here, just add 360 to this number here, making it 364. And then when you subtract 90 degrees from it, it becomes 274. Alright, so you have to visualize it something like this. Alright, now that was a terrible circle. Maybe I should draw one again. Alright, so if I draw a better looking circle, and if this is 360, if this is 004 here, 004, and this is 000, it's also 360, right? So when I say you have to subtract 90 degrees, you basically have to go this way. Alright, subtracting 90 degrees. Now, of course, I should be making it longer. This is 270. So you are basically coming all the way here. And naturally, this will be 274. That's the principle behind it if you didn't understand. Alright, and so your position line becomes, or your PL becomes 094 to 274 degrees. That means that if you draw a position, and this is your observed lat, and this is your DR long, the position line that will pass through this will be in this orientation here. This is the position line denoted by single arrows. This is 094 and this is 274. So your position of the shape is somewhere on this position line. And how do you know what is the position? It can only be found if you intersect this position line with another position line, which you can obtain through the sextant altitude observation. Now we've discussed all this in staggered observations. I have made separate videos on this, so please watch my videos on staggered observations and you will understand how this all falls together in plotting of the position of the ship at sea. Alright, so thank you for watching this video. I will see you soon with some of my other videos. I try to put up a couple of videos or a single video, at least one video per day. But thank you to all my lovely subscribers who have subscribed and they follow me and they send me comments and feedback, and it's mostly all encouraging, so I really appreciate it. If you have anything to say, please feel free to write in the comments and contact me. I'll really appreciate it. Thanks guys.